Welcome everyone to this session on the environmental governance of industrial steam. My name is Santosh Raikar, and as a maintenanologist, I focus on the intersection of reliability and compliance. Today, we're moving beyond just meeting a permit limit and moving toward true operating discipline. We will explore everything from fuel chemistry and multi-fuel boilers to global legal benchmarks and the transformation of our steam islands into sustainable, high-performance systems. Let's start with a hard truth. While we might be making the same steam, different fuel choices have vastly different environmental consequences. While our processes receive the heat they need, the surrounding community often receives the residual risk. A major executive blind spot we face is that fuel purchasing, boiler dispatch, maintenance, and compliance are often siloed. However, a multi-fuel upset doesn't care about silos. It can cross all 5 of these systems in mere minutes, making integrated governance essential. To manage this, every decision must pass through 4 critical gates. Before any fuel change reaches the furnace, we must ask, is it legally authorized? Can our technical controls handle its unique emission fingerprint? Can our monitoring evidence prove compliance? And finally, does the business case account for the total cost, including reagents and potential liability? The ultimate board-level question is, what is our approved fuel envelope? And who actually has the authority to stop a blend that leaves it? Before we dive deeper, a quick note on how to use this deck. This is comparative training, not legal advice. When you apply these concepts, you must always refer to your specific facility permit, your governing document. When benchmarking, we use comparison rules to normalize data, such as dry versus wet basis and oxygen reference levels, ensuring we are comparing apples to apples across different jurisdictions. In our first chapter, we shift our perspective to view the steam island not just as a utility, but as an environmental system. We'll start at the source, the fuel, and trace its path through combustion, controls, and finally, discharge and proof. Consider the emissions path from the source to the evidence. A permit condition isn't just a number on a page. It must be traceable through 5 stages: the chemistry of the fuel, the physics of the furnace, the effectiveness of the control equipment, the concentration at the stack, and finally the data evidence. Here is the executive test. If your mill cannot connect a permit limit to a controllable operating variable in the plant, you don't yet have a functioning operating system for compliance. What happens when the fuel changes? The stack doesn't care about your procurement categories. It simply responds to chemistry. A change in fuel impacts combustion stability, creates specific pollutant profiles, like fuel-bound nitrogen turning into NOx, and generates secondary waste streams like fly ash or scrubber blowdown that must be managed and classified. Different boiler technologies have different environmental lenses. For example, a package boiler offers fast response but struggles with NOx at low loads, while a circulating fluidized-bed, CFB, offers incredible fuel flexibility but requires much tighter control of its ash chemistry and fuel envelope drift. Understanding these strengths and watchouts is key to selecting the right control logic. It's also important to remember that a pulp mill is a complex ecosystem, not a single boiler. Your power boiler, recovery furnace, and lime kiln may all have separate regulatory identities and rules. While a single Title V permit might consolidate them for the regulator, they remain technically distinct challenges that require integrated management. Ultimately, your permit defines your operating envelope. A compliant mill runs within boundaries. On the input side, we manage fuels and load definitions. On the output side, this dictates our dispatch constraints, alarm logic, and maintenance priorities. Staying within this envelope is the definition of operational excellence. To manage these systems effectively, we must speak the language of emissions. We need terms that connect the chemistry in the furnace to the legal limits and the visible conditions our operators see at the plant. Take particulate matter, PM, and opacity, for example. While they are related, they aren't the same. PM is a measurement of mass, while opacity is about how much light a plume blocks. Understanding this distinction is vital because things like condensed water vapor can make a plume look white and opaque without actually being a PM violation. Nitrogen oxides, or NOx, come from three different pathways: thermal, fuel, and prompt. Our control strategy must match the pathway. We use primary controls like low NOx burners to prevent formation in the first place, and secondary controls like SCR or SNCR to treat what remains. Each has its own specific window for success. Acid gases like SO2 and HCl are driven by fuel chemistry. While we can use scrubbers to capture them, we must realize that we are often relocating the pollutant, moving it from the air into a liquid or solid waste stream that requires its own governance. Carbon monoxide, CO, is essentially our combustion quality alarm. If CO is high, it's a signal that your fuel, air, and mixing are out of balance. The fix isn't just to turn a knob, it's to stabilize the fuel blend, restore the air system, and respect the boiler's minimum stable load. Trace contaminants like mercury and dioxins are high-stakes variables. They often determine whether a low-cost secondary fuel is actually a bargain or a legal liability. Because these metals can vaporize in the furnace and condense on fine particles, control requires strict fuel exclusion and precise temperature management. In the pulp sector, TRS and odor are unique performance signals. Total reduced sulfur is more than just a compliance issue. It's a process signal and a major point of community impact. Managing TRS requires a focus on everything from black liquor solids to the availability of NCG collection systems. Regarding greenhouse gases, it's important to note that biogenic carbon is not invisible. While biomass helps reduce fossil fuel exposure, we still have to account for methane and nitrous oxide pathways. Efficiency remains the best strategy because it reduces every fuel requirement, regardless of its source. We must also look beyond the stack. A control project isn't truly complete until we've addressed the transferred impacts: the water used in scrubbers, the solids generated as ash, and even the noise or odors that affect our neighbors. Before we can benchmark performance, we have to translate everything into the same measurement language. This table shows common traps, like forgetting to account for dry versus wet, basis, or the reference oxygen level. Dilution with excess air can make a raw concentration look lower, but the corrected value is what determines compliance. Here's a worked example of oxygen correction. If you measure 45 milligrams of PM at 12% oxygen, but your limit is based on 7% oxygen, your corrected concentration is actually over 70 milligrams. This is why leaders should care. An uncorrected dashboard might look green, while the facility is actually out of compliance. Now we move to fuel and boiler fingerprints. True fuel flexibility isn't just about what the furnace can burn. It's something earned through rigorous qualification, monitoring, and management of change. Natural gas is often seen as the cleanest local profile, but it's not zero impact. We still face risks from NOx, CO at low loads, and methane leakage. From an executive standpoint, never assume that hydrogen blending or backup oil is equivalent without checking your permit and burner capabilities first. Fuel oil provides resilience, but it carries risks for sulfur and metals. Because it's often a backup fuel, it can lead to compliance surprises because it isn't used often enough to stay tuned. Emergency oil firing should be treated as a rehearsed operating mode with pre-qualified fuel and tested controls. Coal and pet coke offer low fuel prices, but they come with heavy control dependencies. When evaluating these, look at the full marginal cost: reagents, ash disposal, and carbon exposure, not just the dollars per million BTU. Woody biomass is a renewable feedstock, but produces real pollutants. The operating challenge is often moisture and fines. We must define our accepted wood very carefully. Clean bark is legally and technically very different from treated or demolition wood. The recovery boiler is a unique beast. It's a chemical reactor, an energy source, and an emissions unit all in one. It requires pulp-specific governance because its performance is tied to black liquor solids and the complex balance of the craft chemical cycle. When considering sludge or waste-derived fuels, the first question is legal, not technical. If a material is legally a waste, you might fall under much stricter incineration rules. A name change on a purchase order won't change your regulatory status in the eyes of the law. Multi-fuel BFB and CFB units offer a wide fuel window, but that window is a control problem. We must approve a multidimensional envelope, bounding moisture, ash, and alkali content, rather than just setting a simple maximum percentage for a specific fuel. In this technology comparison, we see where flexibility meets risk. The best boiler isn't the one with the highest theoretical flexibility. It's the one that can hold its required environmental envelope across the reality of fuel variability. To manage this, we use a management of change (MOC) gate. No trial fuel enters the furnace until legal, technical, and environmental teams have jointly signed off. This no-surprise rule ensures that procurement doesn't buy a fuel that operations can't safely or legally burn. Finally, we need quality control from the contract to the furnace. A certificate of analysis is only useful if it represents what is actually being burned. This requires a robust sampling plan and a clear hold status for fuels that don't meet the specification. In this next section, we focus on controlling the mechanism, not just the symptom. Prevention, combustion, and capture must work together as a single, coordinated protection train. The environmental control hierarchy is our guide. Elimination, rejecting bad fuel at the gate, is always more effective than trying to capture pollutants after combustion. The best environmental event is the one that was prevented at the receiving dock. Our first barrier is combustion control. By managing air mixing and temperature profiles, we minimize the formation of pollutants. This relies on constant feedback from O2, CO, and NOx trends to keep the system in balance. When we use SNCR or SCR for NOx control, we introduce new failure modes like ammonia slip or catalyst poisoning. These systems have very narrow operating windows. If the temperature is too low, you get slip. If it's too high, you might actually form more NOx. Electrostatic precipitators, ESPs, are highly efficient, but they are sensitive to ash resistivity and gas flow. An important watch-out: a powered ESP is useless if its hoppers are plugged. Ash evacuation is just as critical as the electric field itself. Baghouses rely on fabric integrity. A bag leak detector should be your early warning system, triggering an investigation long before a visible plume appears at the stack. We must monitor pressure drops carefully, as both high and low delta P signal potential trouble. Scrubbing for acid gases is limited by chemistry and contact. We have to maintain the right pH and liquid-to-gas ratios. A key executive takeaway here is to inspect for corrosion downstream of these units, where saturated gases can be incredibly aggressive. For trace pollutants, we use polishing controls like activated carbon or wet ESPs. These hybrid trains add complexity to the system's pressure balance, but are often necessary to meet the strictest limits for mercury or fine aerosols. Our evidence comes in three forms: CEMS for direct measurement, COMS for opacity, and CPMS for operating parameters. Remember, a green dashboard is meaningless if your calibration, data capture, and reporting logic aren't also green. To turn equipment into effective barriers, every control needs leading indicators and a verification method. This table provides a playbook for what to watch and how to prove that your controls are actually working as intended. Now we move into the legal landscape. It's vital to understand the architecture of the law before we even look at the numbers. The interplay of federal, state, and sector rules defines your true compliance envelope. In the United States, we deal with a regulatory layer cake. A single boiler might be subject to CAA base authority, NSBS for new sources, and boiler MACT for hazardous air pollutants. Your facility permit consolidates these, but it doesn't replace the underlying engineering requirements. Let's look at the U.S. boiler MACT. It's highly subcategory specific. A small change in fuel or a physical modification can push you into a completely different compliance obligation. Your Title V permit is your ultimate executive reference here. For pulp mills, the rules are even more specialized. Rules like subpart MM for recovery furnaces recognize that these units are part of a chemical process. Governance must span across utilities, recovery, and the fiber line to be effective. In the U.S., many compliance failures happen outside the emission limit. In things like startup/shutdown terms, CMS quality assurance, or missing electronic reports. These administrative details are just as legally binding as the stack concentration. In Georgia, For example, the state's Environmental Protection Division, EPD, incorporates federal standards into site-specific Title V permits. Data governance is an executive responsibility here, especially with the use of GEOs for submissions. In Canada, we see a different architecture. Federal requirements like MSAP overlap with provincial authorizations. While the federal Pulp Air Code is a set of recommended practices, provincial permits, like an Ontario ECA, are the binding legal constraints. Quebec uses very prescriptive source limits based on fuel, size, and age. This makes continuous monitoring not just a digital upgrade, but a capacity-dependent operating requirement for many units. Ontario takes a different approach, emphasizing site-specific dispersion modeling. You model the local impact first, then operate under an environmental compliance approval, ECA. Any modification to the source may require an amendment to that model and approval. In India, we have national standards implemented through State Pollution Control Board consents. While there are national tables for PM, local city, or airshed restrictions can often impose much stricter limits on a facility. Indonesia provides a key legal trap to watch out for. Their generic boiler regulations expressly exclude the pulp and paper sector. You must confirm the sector-specific limits and facility approvals rather than applying the generic multi-fuel formula. Brazil offers one of the clearest frameworks for our industry, with CONAMA resolutions providing specific annexes for pulp manufacturing. These cover everything from recovery boilers to NCG collection and mass per ton limits. China's national boiler standards, GB1 3271, define concentration limits and require automatic monitoring for boilers above a certain size. In key regions, special limits apply that are even more stringent than the national baseline. When we benchmark this legal architecture, we see that jurisdictions differ as much in how they prove compliance as they do in the numeric limits. Whether it's a Title V permit in Georgia or an ECA in Ontario, that document is your primary control tool. This table shows selected numeric examples, but a warning: do not rank these until they are normalized. Different oxygen bases and dry/wet definitions make it impossible to compare a Quebec limit to a Brazil limit without doing the math first. The strongest global systems connect continuous data with reference tests and executive certification. In most jurisdictions, a responsible official or authorized party must personally certify that the data is accurate and the facility is in compliance. What does a violation actually look like? It's not just an exceedance of a limit. It could be a deviation in operating parameters, a failure to maintain monitoring data, or firing an unauthorized fuel. All of these are pathways to non-compliance. In this section, we'll talk about troubleshooting. When an event happens, you must stabilize safely, preserve evidence, and then remove the causal mechanism. The first 15 minutes after an alarm are critical. You must acknowledge the alarm, stabilize the load, and verify if the event is real. The rule of first response is safety first, then protect your compliance margin and data integrity. Always ask, is the event real or a monitor fault? Cross-check with redundant analyzers and process data. If the O2 and CO haven't changed, but your NOx is spiking, you might be looking at a probe or analyzer issue rather than a combustion problem. For high opacity or PM, the likely culprits are wet fuel, high gas velocity, or a failure in your ESP or baghouse. Stabilize the fuel first, then systematically check your fields, compartments, and hopper levels. High NOx is often tied to changes in air staging or flame temperature. Verify your raw versus corrected numbers. Check your reagent flow if you have an SCR/SNCR, and return to a qualified fuel blend if necessary. Acid gas excursions usually point to a fuel sulfur spike or a reagent issue. Stop or dilute the offending fuel, restore your scrubber chemistry, and manage the blowdown to prevent downstream corrosion. High CO signals poor mixing or low furnace temperatures. This often happens during rapid ramps or when firing wet fuel. Hold the load safely, restore the air balance, and re-establish a stable temperature profile. In a craft mill, a TRS excursion requires immediate action on NCG collection and incinerator temperatures. Follow your contingency procedures and be sure to document any community complaints or visible releases. Let's look at a case exercise. In this scenario, rain-soaked bark and an increase in sludge lead to a CO rise, an ESP trip, and eventually an opacity alarm. The question for your team is, which barrier should have stopped this first? Authorization, blend logic, or the alarm response? Moving from a deviation to verified closure requires a disciplined process. Preserve the data, notify the regulator as required, take durable corrective actions, and verify that the problem won't recur. Closure is only reached when both the cause and the reporting weakness are addressed. In our final chapter, we look at leading the transformation. We want to move from end-of-month reporting to real-time constraint management and a culture of disciplined, low-carbon heat. An executive dashboard should show you more than just emissions. It should show your compliance margin, the health of your control barriers, and the status of your fuel envelope. This 24-hour and 90-day view allows you to see repeat deviations and capital risks before they become crises. We also need to distinguish between leading and lagging KPIs. Lagging indicators tell you what happened. Leading indicators, like CEMS uptime or fuel lot acceptance rates, show whether your next shift is protected. If a mill is struggling, we need an immediate recovery plan. Over the first 90 days, we move from emergency stabilization and evidence preservation to root cause analysis, repair, and finally, permanent interlocks and restored margins. This requires a cultural reset from the top. Leaders must state clearly that permit limits are production constraints. We have to stop rewarding output at any cost and start rewarding early escalation of bad news and the funding of preventive maintenance. Looking ahead, the steam island will transform. We'll focus on efficiency, fuel flexibility, and eventual electrification or carbon capture. The goal is minimum cost heat inside verified legal and environmental constraints. When allocating capital, we must fund compliance margins, not just average performance. Use a decision gate that values the consequence of failure and the risk to your license to operate. If it doesn't work at the worst-case fuel or load, it's not a viable solution. Here is a 24-month roadmap. It starts with governance and basic control, moves through standardization and optimization, and finally leads to major technology transformation decisions like electrification. I'll leave you with 5 commitments. Translate permits into controls, use strict gates for fuels, treat CEMS as critical assets, escalate early, and always reduce demand first. The stack is where your plant's decisions become visible. To help with your internal training, we've compiled a video library. Use these to illustrate technology concepts, but always remember that your official permits remain the final authority on compliance. Here are the core regulatory and technical sources used in this presentation. The full URLs are embedded in your speaker notes for easy access during your facility reviews. Finally, we'd like to credit the various open license sources for the imagery used today. Please keep in mind the disclaimer. This is for professional education. Always follow your current legal text and qualified professional judgment at your specific sites. Thank you.